Okay. So, Rishal, am I audible?
Yeah, I can hear you. Yeah.
Okay. So, um, good. Yeah. So, we were talking about this Büchi's theorem in the last class. So, what was Büchi's theorem?
And that any automata can be converted to a EMS, no, some
Monadic second order logic
and then vice versa.
words. So, I mean, it's yeah a bit more. I mean, formally, you can say that every omega regular language is so a language is omega regular if and only if it is MSO definable, right? A language is omega regular if and only if it is MSO definable, right? And so we were, so this was the logic, right? So this was the logic we had. So, uh, so these were the different predicates that we used. And then we also have this thing we were talking about, like if you now consider, let's say, problems which are for three colorable graphs, if you want to define a formula, an existential monadic second order logic formula there. But even an MSO, for example, for graphs, you can consider the predicates. You can have these predicates instead of like Px and x less than y. Now we will have these predicates. So the formula should consist of these the atoms here, and then of course, like yeah, these are the atoms, and then you can take consider the Boolean connectives and such quantifiers, right? First order quantifiers, second order quantifiers, so on. So the formula should use only such things, right? So something which is not uh, part of this syntax should not come in the formula. Okay. So yeah, so we looked at the structure. So essentially the signature gives you what predicates you can use. And for the word model, the domain is over all the positions in the word. And if you have a graph, then it will you will have um, then you will essentially have like the vertices of the graph, they form the domain. Okay, so I think I'll sort of like we talked about all these things, and um, so this was the theorem. So a language is omega regular if and only if it is MSO definable. So this was Bush's theorem, and we looked at the translation on both directions, from automata to logic as well as from logic to automata. Right? Now, suppose if I tell you this thing, give an algorithm that uh, given an MSO formula phi to be interpreted over words, uh, that should check if phi is satisfiable or not.
Okay.
How would you do this?
Like we can convert it to automata and check if the language accepted by the automata is non-empty.
Is non-empty. If it is non-empty, then it is
Then there is
satisfiable. If it is empty, then it's not
yeah.
satisfied. Right? Okay, good. So was it clear, Vishal?
Yes, yes.
Right? So we are asking for an MSO. We are asking for an algorithm which, as an input, will take an MSO formula, and then you want to check whether that formula is satisfiable over the word models. Right? So essentially, it means that whether there exists a word model which satisfies the formula. So essentially, you can then convert the MSO formula into an NBW and check for the emptiness of that NBW. If it's empty, then it essentially means that the formula is not satisfiable. Okay, so that's the thing. Okay, good. So today we are going to start with uh, a slightly different kind of automata. It's called the alternating automata. Okay, alternating automaton, and we will be looking at alternating automaton on infinite words. Okay, so before I get into the formal definition, maybe I can say a few things to give the intuition. Like, right? So we have seen, for example, non-deterministic automaton, right? So far, we have seen non-deterministic and deterministic automaton. Non-deterministic automaton, right? So, for example, you have NFA or NBW, etc. So, if you consider NBW, then what's the idea of an accepting run? You have, like, there can be multiple possible runs, and as long as there exists one accepting run, then the word should be accepted, right? So it's like we talk about, like, there exists an accepting run, right? Right. So, for example, if you say that there is a state Q from which the word AW is going to be accepted, let's say the word AW is going to be accepted like this, right? So then you know that from Q there exists a transition on A to Q prime, and from Q prime uh, the word W needs to be accepted. So which means that Q prime should again have some successor Q double prime, such that if W, let's say, starts with B, then Q prime, you read B, you go to Q double prime, and from Q double prime the remaining suffix should be accepted. So there should again, so it's like at every state, for every letter, there should exist some successor, such that from that the remaining word should get accepted.
Yeah.
Right? So that is like there should exist some success at every state. Now, you can also consider something, I can call it an universal automaton. So we also say universal automaton is one which accepts the entire sigma star. So it's a bit overloaded term that way. Sometimes we also call like sigma star or sigma omega in the case of automaton over infinite words. So a universal automaton can be one which accepts the entire sigma omega. But here when I'm using the word universal, so what I mean is that now from all the successors, suppose it accepts from Q, you accept a word AW. If for all successors, A successors Q1, Q2 like this, you have and similarly for all the states, like for every such state Q, you have that for all A successors, the word will be accepted. And again from Q1 also, it's similarly for all their successors, it has to be accepted, right? And the idea of alternating automaton is kind of a mix of the two. So the idea of an alternating automaton is of the form, it's like I can say now I have two kinds of states, Q for all and Q exists, right? Which will be as if the thing is that some of the states are of this form, like I will call them universal states, right? Universal states, and some states are existential states. Existential states. Okay. So let's say if I talk about let's say you have an existential state. So Q belongs to Q existential, and from Q you have, let's say, three successors. QA, on A it goes to there, suppose Q1, Q2, Q3. Okay, you can write this as a formula in the following form. You can say that as if like delta of QA is of the form Q1 or Q2 or Q3. Okay, so delta of QA is of the form Q1 or Q2 or Q3. So you can go to any of these successors, and from there you can continue to read the remaining circuits. On the other hand, if Q belongs to Q for all, then suppose you can say, well, you can go to all three and you need to accept from all of them, okay, on the A transitions. Okay, so then I can say delta QA is of the form Q1 and Q2 and Q3. Okay, but now you can think of that as if I can generalize more. Okay, so this is already some kind of an universal automaton in the sense, sorry, alternating automaton in the sense that there are states of both these forms. You have states of the form Q for all, you have states of the form Q exists, and it's like the automaton has both kinds of states. And I'm writing this like the existential state in this form with disjunctions, and the universal states I'm writing with the help of conjunctions. And now I can say I can even do more, because see, I have formulas here. Can I do something more? How can I generalize even more? What can I do?
Like maybe concatenate like for a run you can define the logic or something.
Well, I mean, here, for example, I can say that since I'm now talking about formulas here, why not I just talk about something which is even more general, which are like some Boolean combinations over the states, a Boolean formula over the states, right? So I can say, why don't I do something like this? Q1, let's say, and Q2, if I write it in disjunctive normal form, or Q3 and Q4, right? So I'm saying that my states are now even more general. They are not just disjunctions or conjunctions. I can make them something like a Boolean combination over the states, right? I can have such a Boolean formula. And so what does it mean when I say something like this? It means that I can possibly have two runs, right? So I can possibly, so let's now focus on maybe something which is a more general form, which is here. So what does it mean? As if like starting from Q, I can have two different runs, okay? So Q1, Q2, Q3, Q4, okay? And
And
if, yeah, sorry, go ahead.
like either the run from Q1 and Q2 both should be accepted, or the run from Q3 and Q4 both should be accepted.
Both should be accepted, right? So this is what we are saying, and we are going to follow this definition, this most very general definition for defining alternating automaton. Okay, but even somewhere in some places you will see that you have automaton which have seen, for example, non-deterministic automaton, and then you can also, which has existential states. You can also think of automaton which will have universal states, and then you can think of automata which will have both of them together, that you can say as an alternating automaton. But this is somewhat even more general, right? When I'm putting them as Boolean combination of formula, right? So the transitions now you see, they are no longer just going to some state, but this is a Boolean or more formally like positive Boolean formula over states. Why positive? Because there is no negation over the states which are appearing, right? In general, when you have atoms, like you say A or negation of A, like which are called the literals, right?
Yeah.
If you have a variable X, Y, Z, you can say not X, but those not X kind of things, they are not appearing here. So this is like a positive Boolean formula. Okay. So now your transitions will have such positive Boolean formulas.
So don't allow negative things in the.
We are not allowing. So in general, for example, if I say like I can dualize the transition, which we'll see, like when we are going to talk about, for example, negating such alternating automaton. Like how do you get a complement for the alternating automaton? Then you might need to dualize the transitions. But when you are dualizing the transitions, we are still not going to put a negation of the Q, because that doesn't really make sense. Like what we are saying, that you have the disjunction and the conjunction. So you may want to say, like, I can replace the conjunction with the disjunctions and the disjunctions with the conjunction. Something like this you can say, right? But putting a negation on the Q doesn't quite make sense, right? I mean, it's like, so these are somehow called, these formulas are, in some sense, we would call them obligations. Like, so this is the obligation for state Q, that on A, what it needs to do, how it needs to proceed further, right? So that is the obligation for Q upon reading A. This is what it should be able to perform, right, in order to accept further. Okay, so that's the thing. Good. So I'll now
these have to be non-deterministic, right? Or
So-
is that trigger?
it's not. So the idea of alternating automaton is that it's not just non-deterministic. So essentially, what I was saying, that when you talk about a non-deterministic automaton, right? To start with, you have existential states, and so which you can write it in this way. So if you say, for example, Q belongs to, like, it's an existential state, like in the case of non-deterministic automaton, what you say is that some run from the successor, from one of the successors has to be accepted, right? So that is what a non-deterministic automaton says, right? So for example, on A you have three successors, you can write it in this form, Q1 or Q2 or Q3. So it means that the word AW can be accepted if from either of the successors W can be accepted, right? So that is the idea of a non-determinism. If instead I say that all the runs should be accepted, so if I have a word AW, correct? So I should say that my state Q, this is a universal state if for all successors, right? For all successors Q1, Q2, Q3, which you reach by reading A, from all of them, if you read the W, they should be accepted, and so on, right? So that is the notion of a universal state, right? Now the existential state, you can write it in this way. It's like a disjunction. The universal state, you can write it in the form of a conjunction, Q1 and Q2 and Q3. But then you can say that, well, if I have both the states, both kinds of states in an automaton, that is like an alternating automaton. But you can go even more general. I mean, you can write things even more in general form, like it can be a Boolean combination of such formulas, right? It can be like this. So here it essentially means that you can have two different runs. One run in which you have to accept along both Q1 and Q2, another run in which you have to accept along both Q3 and Q4. Right? So it's not just non-determinism. It's
Okay.
more than.
So it doesn't have to like transition to all Q1 and Q, like all the next ones. Just that it has to accept if it goes there.
So the transition relation is defined like this. It's defined in terms of these formulas, right? So when I say that, like if I give you the transition relation like this, then this is what is going to define your sort of, when you draw your automaton in terms of this, you put the edges, you will put the edges like this. That, okay, you can have, these are the different successors, A successors, and if you want to accept, you have to now continue from this as well as this and accept from this as well as from this, and similarly from here to here, right? And again, how you will accept from each of them, that depends on they are formulas, the Boolean formulas which are there with respect to Q1, Q2, Q3, and Q4. Right?
Okay.
Okay. So maybe I think we will look at some example and then I think it will become clearer. So the idea is that the transitions now, the transition relations are not just like a non-deterministic automaton. Like we are not saying how do you do it in the case of a non-deterministic automaton? Like delta of QA, it's a subset of 2 raised to delta is a function, right? Delta is a function which is q cross sigma to 2 raised to q, correct? But here we are not saying that anymore. Now we are saying that the delta is a function which takes some element from q, some element from sigma, and gives you a Boolean formula over q, right? So I'll write it in a positive Boolean formula, right? So we'll see this thing in a while. So let's go over some definition to start with. So for a set X, what is X? X is a set of variables, right? And I'm saying B plus X is the set of positive Boolean formulas over X, right? And it can use this conjunction, disjunction. So we also have formulas which are both true and false. So we are also going to use true and false. So if you say something is true, right? For example, delta QA is true, that means it doesn't have anything more to sort of satisfy. So it's kind of like, okay, once you have reached there, delta of QA is true, that means everything is kind of is good. So you are going to accept from there. So once you reach the Q, you read an A, it's like an accept. So every, like all the infinite suffix, the entire infinite suffix starting from that A is going to be accepted. So
Even
true is.
the neighboring state has some constraints.
So what is the neighboring state having some constraints? So here I am saying that the definition of your neighboring state is defined by this formula, right? There is no such separate neighboring state as such. That is given by this formula. Even this is the case in your NBW also. The transitions define what are your neighboring states. The neighboring states are not the primary thing. It's the transitions which will define what are your neighboring states. Even in the case of an alternating automaton, also it's like this, that your neighboring states are going to be defined by the Boolean formula, positive Boolean formula, right? So now, yeah. So if you say, for example, if I say delta QA is true, if I say this, it's true, then what does it mean? It means that now anything A followed by sigma omega, Q accepts the language. The language of Q, so that means all the words which are accepted from Q is anything A followed by a sigma omega. Because after A, you don't have anything else which is there as part of your obligation further. So true means like everything is good. Okay. On the other hand, false means that no state satisfies false. So no state satisfies false. So if you have delta Q comma A equal to false, then the semantics of that is essentially like from Q, you cannot go to any state because no state is going to satisfy false. So you cannot take a transition in. This is not allowed. Okay, because if you are going to some state, from there you have to do that remaining obligation, right? Yeah. So you cannot take that transition if it is false. Okay, so that's okay. So we say that Y satisfies a formula theta belonging to this B plus of X. In particular, we will be using P plus of Q, right? This is what we were seeing, right? Our variables, the X variables are nothing but the variables which are the states, correct? So that is what we are going to do. So we say that Y satisfies a formula theta, a positive Boolean formula. B plus X is the set of all positive Boolean formulas. So theta is such a positive Boolean formula. If and only if the truth assignments that assigns true to members of Y, right? So we are saying Y satisfies this formula theta if for all variables which are there in Y, you are setting them as true, and whatever is there, the remaining variables which are not there in Y, you assign them false, right? And if that should satisfy the formula theta. Okay, so then we are saying that Y, this subset Y satisfies theta. Okay, and we also say that Y satisfies theta in a minimal manner. Okay, in a minimal manner if no strict subset of Y satisfies theta. Okay, Y satisfies theta in a minimal manner if no strict subset of Y satisfies theta. So, why are we defining all this like this minimal manner? What do you think? Why are we?
Finally, we want to look at alternating automata. So, if you have a formula like Q1 or Q2 and Q3, then it makes sense to just look at the minimal possible constraints.
Correct. Because you can have multiple possible runs, and as long as there exists some run, right? If you have Q1 or Q2 or Q3, so for example, like as you were saying, suppose if you have Q1 or Q2 or Q3, right? Delta of Q comma A equal to this, it may be possible that the formula may be satisfied by having, right? And as for example, in this case, like you can set to any subset of Q1, Q2, Q3 to true, right? But what we are looking at, like when or what we are interested in is that when a word will be accepted, as long as there exists some accepting run.
Yeah.
So if there is an accepting run from Q1, we are good. If there is an accepting run only from Q2, we are good. If there is an accepting run only from Q3, then also we are good, right? So that's why we are looking at this minimal satisfying in a minimal manner. Okay, that's the intuition. So for example, here if you have, you can consider the sets Q1, Q3, Q2, Q3, as well as Q1, Q2, Q3. All these satisfy this formula Q1 or Q2 and Q3. Okay, but these two sets satisfy the formula minimum. So I can say that as long as I have a run, okay, for example, which will have Q1, Q3, or I have another run which goes from Q to Q3. Okay, so I'm fine. If one of the runs is accepting, then I can say that the word will be accepted. The corresponding word will be accepted. Clear? So is it clear for the online participants? Any question?
Is this formulation more powerful than one where we would, just have Q1, Q2, Q3, or like Q1 and Q2 and Q3? Like you partition it into existential and universal things. Or
Yeah, that's a good question. So I did not think about this, but I believe that this will possibly their equivalent. I would think so, but I need to check because I mean if you allow epsilon transitions, then this is possibly true. But on the other hand, for example, if I say, let's say if I just consider this thing, okay? So delta of QA, I mean exactly this thing. So let's say we have this Q1 and Q2 or Q3 and Q4, right? So, so I'm saying that you can have both of them, now you can have both such accepting runs. Now the question is that how would you like to so if your initial state is like this, so if you have the q, small q is the initial state, how can you write this using just the universal and the existential states?
Yeah.
So let's say everything is accepting from here. Right? So this is like you just have some transition sigma, like on the sigma you are just accepting everything. So now one of the things here, I think what we are going to say is that I will have a single initial state, right? In general, in NBW, we saw that you have a set of initial states is what we were starting with, right? So the reason for not considering that is because if you have this, then I have some special status for the initial set of states, in the sense that I'm saying that it's like a disjunction over these initial states, right? I'm giving like the existential states, I'm sort of making it somewhat I'm saying that the set of initial states, they form some kind of a disjunction. Do you see? Like if I say, if I have a set of initial states, then you say suppose Q0, Q0 prime or whatever, Q0 double prime, if these are my initial states, then it's like there is a formula which is like it's a disjunction of these things, right? So I don't want to say that, and I say that suppose there is a single initial state which I have, which is like Q0, and then it becomes kind of uniform. Like I have both the I have both these. I mean the formula here can be a Boolean formula over the states. Now, is it equivalent? Like, can I?
Yeah. Maybe we can add one state in between and put an epsilon transition to it.
Yeah, with the epsilon transitions, I think, but here we are not talking about any epsilon transition.
Yeah, without it, it might not work.
Yeah, without the epsilon transitions, I don't see immediately how, but I'll think over this. That maybe you also can think over this, like whether it is possible.
Yeah.
It should still work, right? Like if there's a formula associated with Q naught,
Mm-hmm.
we will just consider the same with that single initial state.
Mm-hmm.
And then there is some formula associated with Q naught prime and with Q naught double prime. You will just do the OR of all those formulas.
Right. So, for example, I mean, if I tell you about this particular formula, Q1 and Q2, or Q3 and Q4. So, what he's saying is that, like, can we consider them as, like, here it's a Boolean combination here, right? You have both disjunction and conjunction. Now, if I say that if I just restrict my states as either universal state or existential state.
Okay.
Okay. So, I allow from my states only disjunction or only conjunction. I don't mix them.
Okay.
Right? Now, is that model a strict subset of this model, or is it equivalent? That's the question. Okay. So now suppose if I have such a formula, now without using any kind of epsilon transition, can I still translate that into disjunction or such things, right? So this is something yeah, right? I mean, we need to see. Yeah, it may be possible, like, yeah, I need to think about this a bit. Like, it may depend on, for example, how things are happening from Q1 and Q2. Suppose there is some transition which is going from Q1 and some transition from Q2. Can you directly go from your Q to those transitions and things like that? So I think I'll think over this, but you can also think over this. Like, so, okay. So, yeah. Okay, good. So, yeah, so we were talking about this satisfying in a minimal manner. And so this is what I said in the beginning itself. Like, so if you have non-deterministic states, like non-deterministic transitions, then you can say that, okay, it's like the delta Q, it's Q1 or Q2 or Q3. Then you may say some run is accepting. It's like the standard non-deterministic existential states in non-deterministic automaton. It can be written as a disjunction, and universal states where all from all successors you have to accept they can be as conjunctions like this. And here we are considering arbitrary forces. Okay. So we looked at this example. A word of the form AW is accepted from Q if and only if W is accepted from both Q1 and Q2 or from both Q3 and Q4. Okay. So we are combining both of these things. Now, how does a run for such an alternating automaton on infinite words would look like? How does a run look like? So you have, for example, like we were saying, that a run now can correspond to this part or a run can correspond to this part, right? So now you see that the run would have some kinds of branching starting from Q. When you read A, you go to two states, Q3 as well as Q4. And similar branching can happen. So it forms the run essentially gives you a tree. So we'll call it a run tree. Instead of the run being a single word, now the run itself, it looks like a tree. Okay. So, and I said in the beginning that
Loops are not allowed in the thing, right? Like, it doesn't make sense.
It can make sense. For example, like if I just say, like if I just have a formula of this form, so just delta of QA equal to Q. It's also a Boolean formula.
Alright, so
Delta of
from
QA
Q,
equal to
we look at the remaining word and then.
right? Or you can say delta of QA equal to Q and Q1, right? So then what do you have? You have from Q, you can have a self loop, as well as you are going to some state which is Q1. So you have to satisfy both of them,
Okay.
right? So a self loop can certainly be there.
Okay.
It's a Boolean formula, it's a valid Boolean formula, it can be there. Right? Okay. So, and I said that why we prefer to have a single initial state rather than having multiple states is because, like, if you have the standard convention of having a capital Q0 as a set of initial states is like there is a disjunction. So you are saying that I am particularly having a disjunction over the set of initial states, but to avoid that, we are saying that we'll have such which is more general, okay, and we can have a formula corresponding to that. So what is a tree formally? So as I said that a run of an alternating automaton is a tree. What is a tree? A tree is a prefix closed state. It's a prefix closed set T, which is a subset of n star. So what is the idea of n star? So why I'm saying it's a subset of n star? Like, so this set T, it has the set of nodes of the tree. It has a set of nodes of the tree. So essentially, when I say n star, so you can uh, like put some natural number one after another, okay, and it's like a concatenation of such natural numbers. It's just like sigma star, right? So for example, how does a node n may look like? A node in a tree may look like, let's say, it may be of the form 0, 3, 1, 2, like this. Okay, all concatenated. So what does it mean? If I say a node is of the form 0, 3, 1, 2, etc.
Like 0 and 3 are connected in some
0 and 3 are connected in some
and 3
way.
and 1 and 1 and
Of course connected, but what is the semantics? Like a tree, you know, all of you know, right, how a tree looks like. I mean, a tree will look like, for example, a tree will be very much like this, right? So like this, and similarly it will have branches, then it may have some branches here, some branches here, right? It's like this. So when I say 0, 3, 1, 2, which particular node I am referring to? So what is the idea? So I can say that, so these children of a given node, so starting from this I will refer to as epsilon because it's n star. So I'll refer to this one, the root node, as epsilon. And then 0, I will say that the 0 is like, maybe it's kind of some ordering is there for the children, for the, right? So this is 0, then let me write like 0, 1, this is 2, this is 3. Okay, then I can say from here you can again have a 0 and a 1. I can again have a 0 and a 1, right? Like the left side is 0, then this is 1. So this is like, and here also I can have, I can similarly have these directions. So let me try to write it. So I can again have this direction 0, 1, 2, 3. So these are like directions, like instead of just left, right, if you have multiple children, you can have this direction 0, 1, 2, 3. And 0.3 maybe is this one. I'll say this is my 0.3. Okay. Similarly, now I will say this is my 0.3.1. This node is 0.3.1. Okay. And from here, I can again have, let's say, this can have different children here. So this is my 0.3.1.0, 0.3.1.1. This will be my 0.3.1.2. Okay, so this is why we are saying that these are the nodes, right? So this is an element of the set T, right? So T is a subset of n star. So each such element belongs to the set capital. Okay, and if x dot c belongs to T, if x dot c belongs to T, where c is a direction, right? Where x is of the form n star, c belongs to x belongs to n star, c belongs to n, then x is also empty. If you have a node, then you have your predecessor. The predecessor is also in the set. Correct? So that's how we are defining formally a tree. A tree is nothing but a prefixed closed set of this form. Is it clear, the online participants? Is it clear, the definition of a tree?
Yes.
Yes? Okay.
Yeah.
Okay.
DAG would also be prefix closed.
Sorry?
Wouldn't the DAG also be prefix closed?
Exactly. Okay. The DAG is also a prefix. It's prefix closed indeed. On the other hand, like we will say that in the case of a tree, like you have a unique path for reaching an element. So one of the things, if you consider a DAG, then what can happen is like one given node can have different, like, I mean, one given node may have different levels, in the sense, like here if I say that my set. So for example, a node 0.3.1.2 is different from 0.3.1.1, and so each of them is unique. So it's a set, right? So it's a set. So each of them is an element. Whereas in the case of a DAG, you may have different paths, right? Like, so when you are reaching a particular node, let's say you go like this, go like this, but then you can come here, right? Now how are you going to have the label corresponding to this particular node, right? So you can either call them, let's say, call this thing as 0.1.0, or you can call it 0.2.0, right? Right.
Okay.
So that is here in the case of a tree, you have all these nodes and they have like a unique, it's a set, right? So each such node has a unique label. Okay. Right. So, and then I say that the empty word epsilon is the root of the tree. And so for every x, so we say x dot c for c, which is a natural number. It essentially gives a direction, right? We say it that c is a direction. It's a successor. X dot c is a successor, and a node is a leaf if it has no successor, right? Even though the run we are looking at, for example, infinite words, it can be possible that there is a run which actually has some path, like the run itself is a tree, but some path of the tree is actually a finite. It's a finite path. Why is it the case?
Because it can happen that after this point there is no valid transition with that symbol, or the node is a true.
If there is no valid transition, then it will not also be a valid run.
No, I meant like the prefix till now is fine.
Huh.
But then after this, there's nothing we can extend it.
Yeah, if you cannot extend it, then it's like the run cannot extend further. So hence, I will say it's not even a valid run. Because it cannot extend, right? Sorry?
You are only considering the valid
I'm
runs.
considering valid runs, and I'm saying even then also I can have some path.
Because maybe that's a true.
That's the true, exactly. Because true refers to valid runs,
Okay.
and then which are like the runs, and the true can lead to a finite. Like if you have this note which says there is a true, then you know that there is nothing more which needs to be satisfied, and the run, the corresponding to that, the path corresponding to this run it will end there. It's a leaf there. Okay. Right. Good. So right, so we can say a node is a leaf if it has no successors, and in fact in a run, as we said, that there can be leaves, and a path pi, which is a subset of t. So t is a set of nodes, and the path is also a set of nodes. So a path phi is a subset of t, such that for x, which is a node in that path, either x is a leaf or x dot c belongs to pi for a unique c. That unique c is important because in the path we are saying that you have only one successor. A unique successor is there in the path, right? So there is a unique c. So if I have, let's say this is x, then there is a unique c such that x dot c is in that path. I cannot have two different c's, c and c prime in the path. That's the thing. And what is a sigma labeled tree? A sigma labeled tree is you have a labeling function on the tree, which is R, and R maps from T to sigma. It's a labeling function mapping each node to a letter in sigma. Okay. And in particular, when we are talking about a run, right, a run tree in this alternating automaton, then what is the labeling function? How will it look like? It's a what label tree? Sigma label tree. What the sigma is going to be?
Sigma is going to be but in that each edge should be labeled with it's something in sigma, right? Because like we have transitions.
So for example, here when we were saying earlier, right,
Okay, it will be a logical formula.
it will be a logical formula, but the logical formula can correspond to multiple runs, right? Like as we saw that the logical formula here or here maybe, right? Here, this may correspond to multiple such runs. There are, for example, at least I can talk about like this. I can talk about these two runs here. One run is like this, the other run is like this, right? And I'm just now we are talking about a run tree where we are looking at one single run, right? And we can have such the whole tree it will just continue, right? There may be some leaves, there may be some paths which can be infinite paths and so on. And how are so when we are talking about the labels here, what does it label? It labels the nodes, right? It labels the nodes with sigma.
Yeah.
In the case of a run tree, how are we going to label the nodes? From which set? What will sigma be? Yes.
So sigma is Q basically, right?
Sigma is Q, exactly. Sigma is capital Q, right? So we are reading the.
Oh, right. Okay.
Right?
Yeah.
Sigma is just capital Q. See, so this is my tree. So I may consider my tree like starting from Q. I can have Q. I can go to one run is like this. On reading an A, I'm going to both Q1 and Q2. So this was my tree, right? The nodes are actually this. They belong to N star, and they're labeled with the nodes are labeled with this with letters with elements from capital Q.
Okay.
Right? It's a Q labeled tree. It's a Q labeled tree. Clear? Okay. Good. Right? So here, so I say run of a word W, which is of this form on alternating automaton. It's a Q labeled tree. Okay? TR. Right. Right. So just okay. So it's a Q label tree. So it will have some properties now. So what are the properties? So yeah. So one is that note that epsilon has to belong to the tree T because that is the root node, and you have R of epsilon is Q0. Okay, because this is the starting state, the initial state. R of epsilon is Q0. And suppose if it is the case that X belongs to T, okay, and then you have suppose R of X equal to some Q, right? It's a Q level tree. So if there is a node X with R of X equal to Q, and suppose delta of Q equal to theta, it's some Boolean formula theta, then what happens? Then there is a set S which is of the form Q1 to Qk such that S satisfies theta in a minimal manner, right? Because we are talking about a single run, it satisfies theta in a minimal manner. And what else? What else? How should the successors of Q look like? How should the successors of Q look like?
Like, it should be Q1, Q2, Q3.
Exactly. Yeah.
But I'm not sure how the logical formula can be. Like in the sense we will have those neighbors.
Right.
Uh,
So you are satisfying them in the minimal
oh,
manner.
okay.
So
Okay.
that means they are in conjunction
Right.
somewhere, right? Q1 and Q2 up to QK, they are in conjunction.
Okay, and if they are satisfied, the formula is satisfied. So
Yeah. So you will have, for example, now in the tree from Q, you will have successor nodes which will be of the form like QC. So
Right.
it's like for all C of this form, right? We have X dot C also belongs to T, and R of X dot C equal to QC. I mean, it was slightly QC plus
QC only.
QC only. Right. Because C is from 1 to K. Yeah, I mean, I was writing that time the direction is from 0 to something, but yeah, that's the. Okay. Okay, is it clear? So if you have that, if you have this set which is satisfying in a minimal manner, that means they are in conjunction, right? Then you will also have in the tree, you will have those successors like X dot. For each C, you will have X dot C in the tree, right? X dot C in the tree, and their labels will be like R of X dot C is that case. Okay, so this is how the run looks like. Is it clear? Okay, and I mean, just to give you an example, so if you have something like this, then you have a root which is labeled Q0, then at level 1, level 1, you have two nodes. I mean, so maybe if I consider, let's say, two nodes, and let's say I can have Q1, Q3. This is a valid run, okay? Or I can also have, let's say, if I consider another run, then Q2, Q4 can be another possible such run, which will minimally satisfy this, and so on. The other thing is that, like, if theta equal to true, then what? If theta equal to true, then what is the thing? Then, sorry, then X does not have any children. Okay. If theta is true, then I don't need to satisfy anything more. Everything is fine from then on. Okay. So hence, the may have leaves. Okay. So TR may indeed have leaves. Okay. Now the other thing is that to note that no set S satisfies false. Okay. So nothing satisfies false, right? Hence, there cannot be a run with a transition with theta equal to false. Here. Okay. Any questions? So this is, we were defining the run corresponding to an alternative automaton. Okay. One single run. Looks well. Now, when shall I say that a run is accepting? Now you see that a run can have infinitely many paths, right? A run can have, it's a branch, it's a tree, and some, of course, some paths of the tree can be finite, but in general, it's also possible that some paths, like many of the paths, can be infinite. And how many paths can be there? There can be infinitely many paths, right? And we are saying that a run tier is accepting. When will it be accepted? If all the paths are
Satisfied.
all the paths are.
Like
So we started with, so I don't remember if I say, right? So our alternating automaton looked like this. So we were talking about alternating Büchi automaton. So we also have an alpha here, right? We also have an alpha, right? So if you consider, let's say, a universal automaton, let's say. So when I'm talking about one single run, right? It's like everything is in conjunction. So from all the states, always whatever you are, when you are minimally satisfying, all the infinite paths need to be satisfied. Correct? Because it's in some sense we are saying that once you choose the run, then they are in conjunction. If you have disjunction, they will correspond to different runs, different possible runs. Right? In a single run, everything is in like conjunction. Now you say that it will be accepted, like when in that path, when in a path, since it's in conjunction, the states in alpha will be visited infinitely often, right? So hence we will say that a run tier is accepting if and only if all of its infinite paths. See, I am not talking about the finite paths because finite paths are anyway good. We know that finite paths for a valid run, for any run, it will end in true, so they are good. We are left with the infinite paths. See, if all the infinite paths, because since we are talking about conjunction, all the infinite paths should visit alpha infinitely often, right? Which all the infinite paths which are labeled by words in q omega are accepting, right? So that means all the paths, so every individual path should visit alpha infinitely often. That's the thing. And we say a word is accepted if and only if there exists an accepting run of turtle. Okay. So conjunctions essentially, like if I say the disjunctions, as I was saying, it gives me individual runs. Clear? Disjunctions, that gives me individual runs, whereas conjunction gives me the paths of the tree. Right? Yeah. So when I'm talking about a single run, then I will have these conjunctions, right? Which will give me the paths of the. Okay.
But run itself is a tree, right?
Run itself is a tree. Run itself is a tree. You are right. So what is the question?
So then conjunctions would be a tree as well, right?
Yeah, I mean, for example, now when I say that there is a run, then I mean you have already kind of resolved the disjunctions. So suppose if you had Q1 and Q2 or Q3 and Q4, so you are in a run, you are either considering this part in a run, or you can consider another run in which you are having this part, right? So if delta QA is of this form, then what it means is that from Q on reading A, there is one run which goes to both Q1 and Q2, another run which goes to both Q3 and Q4. So this is a different run. So this is one run, this is another run. But this is also a tree, this is also a tree. Right? Around Q labeled tree. Capital Q labeled tree. Does it answer your question?
Yeah.
Right? Good. So now we will look at some example. Okay, so this is something you should try yourself, and yeah, let's do this. So suppose there is a natural number n, and sigma n is of this form 1 to n, right? And I am talking about I would like to design an alternating Büchi automata, right? Like, so I'm telling you the language, and what you would like to do is to define the alternating Büchi word automata, right? So what is the language here? So this ABWAN, so this is parameterized by n because sigma n is from 1 to n. So this is my alphabet. It accepts all words with the subword. So I, right? So I, this thing should appear for all I. Okay, for all I should appear. This it's called, some people also call it a factor instead of a subword, but for all letters I. Clear? Okay. Right? So they are they follow one another, like 3 contiguous i's for all i's. So that should appear. So for example, if your I is 3, let's say, then you should have a word, let's say, sorry, if your let's say n equal to 4, let's say, then you should have 1.1 somewhere, 2.2.2 somewhere, 3.3.3 somewhere, 4.4.4 somewhere, right? And you can have something else here in the middle, right? So, but these 4 patterns should appear in the word, right? Now the question is, how can you construct an alternating Büchi word automaton to accept this this language? Okay. So can you try for a couple of minutes and think about this, how you would like to define the right here. So what should be the crucial idea?
Firstly, we should have 4 transitions from the initial state, one corresponding to each I.
Very good.
And then in each of the things, we need to ensure there is some I think of the ring.
Yes, absolutely.
Now, how to ensure that?
Yeah. So I think you say the main idea. So let's try to formalize this. So what I will do is, like, I'll say that I'll have a state space which is Qn, okay, and Qn is of the form, like, I'll have an initial state to start with, which is Q0, and I'll have sigma n cross 1, 2, 3, like this. So what is the idea of this? Like, so these are the states, right? So these are also the states. So that means, so if I have, let's say, a state of the form I, C, where C belongs to 1, 2, 3, then the state IC, right? The state I, C, it waits for reading
3 C's, like CCC.
Yeah, like C1 can be, okay, if you want to write it this way, I can just change it to, if it's easier for you to think this way. So so um for reading IC. So it's a bit difficult to understand what I'm saying is that like the state IC will wait to read C many I's contiguously. C many I's contiguously. Right? So this is what it means. C many I's contiguously. The state IC waits for reading C many I's. And once it reads, like once you are in I comma 1, right? You just need to read one more. So 2 I's you have already read contiguously. You have reached here. And then after this, if you read an I, then I will say I have satisfied. I don't have any more obligation. So I will, my corresponding formula should be true. Right? And every time, if I am at IC, and then I read an I should be going from I to C minus 1 for C in
C2 or 3.
C in 2 or 3. Okay, so that is the idea. So now let's just try to write this a bit formally, which is like, so from the initial state, if I read this delta of Q0 comma I, I'll go to, so I have already read 1 I. So I'll go to I comma 2. And as you said, like I also need to read the other letters. So I can go to all of them together, right? And I will say J not equal to I. I'm reading the first I letter, J not equal to I. And this is
J comma 3.
J comma 3. Very good. This is J comma 3. Clear? So from here I'm going to read the other things. But now if I say that it happens that I am at some I comma C, right? If I am at some I comma C, just to write this, if I'm at some I comma C, but now if I read a J from here, then where do you go?
I comma 3.
Then you go to I comma. Very good. Okay. So let's now write down this a bit formally. So we have understood the transitions, the idea. So I'll just, so this is the first transition I think I already wrote. Now I will write the other ones. So which is like if delta m, so I'm saying, suppose I call it delta n, just like qn, so my transition. So my automaton is of the form following, like the automaton, the alternating automaton that I'm going to define, it's like qn sigma in q0 delta empty set. Why my alpha is empty? Because I'm going to accept for all the paths, I'm going to accept with true, the true, right? I don't have any particular state which I need to visit infinity of. Okay, so delta n, and I say delta n. Just I'm now trying to formally write down whatever we discussed here. Delta n of IC comma j equal to IC minus 1 if what?
If
J
J is
equal to I and C belongs to
2 or 3.
2 or 3. Good. It is true if
C is equal to 1.
J equal to I
J.
and C equal to 1.
Yeah.
Okay. And it is I comma 3 if J not equal to 1. Okay. And here one thing just as a remark, that all copies, when I say all copies, I mean like, so there are these 3 n such branches, right? So all these this corresponding to each letter. So that's what I'm saying, like a copy. A copy corresponds to a letter here. They have to go to go to true, right? In order to, I mean, which essentially guarantees that I dot I is indeed red for all I in sigma. Is it clear for the online participants? The definition of the automaton which accepts this language. Any question?
No.
Is it okay?
So in the tree, there will in the run of this automaton,
Right.
we will not have any infinite path which accepts. So every
No.
accepting will be finite paths, right?
The accepting run will be a finite.
Finite tree. Yeah.
Yes.
Yeah.
Right. If you have, for example, like a word which is which is in the language, corresponding to that you have an accepting run, and that accepting run will be a finite. Because all the paths they will end at 3.
Also, if there is some infinite run, because our alpha is empty, like how can we ensure that it is not accepted? Because according to the definition,
So how? Yeah. If so, what does it say? It says that okay. So So, for example, if there is a word which is not there in the language, right? And you have a run corresponding to that, and let's say I just have something like 1 2 omega, something like this, right? And now what will happen corresponding to that? So how will the run tree, how will it look like? So let's see. So you have, so initially I'm going to, so I will always go to these states like J, this. So I am writing the I for this letter. So I'll always go to I comma 3, I comma 2, and then like for the first, for I equal to 1 and 2, that will alternate. And for the other ones, I will always be at 3, right? So, and then it's going to give me like an infinite run.
Yeah.
And so if I have that infinite run, then yeah. So by this definition, it happens that it is going to be accepted.
Yeah.
Which is not correct.
Yeah.
Right? Okay. So yeah. So right. Okay. So I have the true.
Maybe we need to ensure, like we need some state of the form I comma 0 or something. I don't know. And it should visit that state infinitely often.
Yeah, you can do that. I mean, one can do something like I can say instead of true, I go to I comma 0, and from I comma 0 on every sigma I get I comma 0.
True.
So instead of true, if I want to say something like, say I will go to, let's say I also have let's say a 0 also here. So let's try this. And then I'll say that instead of true, I'll go to, let's say I comma 0. And then I say from I comma 0, whatever I read, I always stay at I comma 0.
But the set of accepting states is the empty set, right? Like does so in
That will be I comma 0.
Yeah, right now we are saying that the set of accepting states is the empty set. Like this is what originally I was saying. But then what she is saying is that now suppose if you have a word like this, which is not supposed to be in the language,
Okay.
right? Then you have the run and it's not visiting. I mean, like you don't have any alpha state, right? And what is the Büchi acceptance condition? It says that a word, for example, is accepted if some state. No, I think we are still fine. We are fine.
Because if we take intersection with empty set,
Fine, right? So
then
what is the Büchi acceptance? How does it work? Right? So the Büchi acceptance is like, it says that inf of R, so if you have a
It's having a empty.
intersection alpha should not be empty.
Okay.
Okay, since your alpha is empty, so this is empty.
Yeah.
Okay, so then we are fine. Okay,
Yeah.
good. Thanks. Yeah, thanks, Risha. Okay. Okay, good. Yeah. Okay, so then I think we are convinced now that this indeed works. Okay. So now if you think of just think about this, that we are defining an alternative Büchi word automata. Instead of this, if I consider an NBW to accept this language, right? If accept this language. So what do you need to remember in that case, in the state space? So you have to say that I have seen 3 consecutive eyes for all such eyes, and they may appear in any order, right? So what you need to remember if you are talking about an NBW, that for which all eyes I have seen these 3 consecutive eyes, for which all eyes. So the different subsets of these sigma n that we have seen so far, right? So something here to note is that the number of states that we have it's linear, right? Like linear in the size of the alphabet. So we have only 3n plus 1 states. Correct? 3n plus 1 states. Whereas if I'm considering like for which all eyes, like I've seen already 3 such things, then intuitively I would have to remember something like 2 raised to, n such subsets, and the NBW may have so many states, right? So you can try to show formally whether, can you come up with some arguments which will show that any NBW that accepts this language should have exponentially many states, right? We've seen such arguments, some examples. I think the more difficult part is to come up with the family of languages. But now, given that we are talking about this family of languages, it should be relatively easier, given that we have seen such proofs, that whether we can prove formally that in will have so many states in it, right? Any input. Okay, so I'll just quickly talk about. We still have 5 more minutes by this block. So we'll talk about closure properties quickly. So what about the union? So the union of, we will first say that indeed this is closed under union. Okay. So I can think of an automaton A, which accepts the union of the languages of A1 and A2, as like, so I'll have Q1, Q2. I'll have a special initial state which I'll call Q0, okay, and I'll have this sigma delta. Q0 is the initial state, alpha 1 union alpha 2, okay. So here we are just, since we are allowing arbitrary formula, we are having such a single initial state, okay. And then the idea is the following, that what am I saying? So I have one ABW, right? Like a run from there. Okay, I have one alternating Büchi word automaton, so which has a Q01 as the initial state, and you can have such run tree from there. You can have another alternating Büchi word automaton, which is the A2 here. There is another run here. Now you see that from here I can actually read, let's say from Q01, I can read an A here, right? And I go to some set of states. Similarly, from Q02, again I can read an A, I can go to some set of states here. Now, if I introduce an initial state which is just Q0, correct? So how should the delta of Q0 comma A look like?
The delta for Q0 1 or the delta for Q0 2.
Sure.
Like the
Yeah. So this will be delta of Q0 1 A
or delta of Q0 2
A for all A belonging to sigma, right? So this is how the delta should be defined.
Yeah.
Clear? Is it okay? The online participants? Is it okay? The definition. So from the initial state, we should actually consider the transitions, the A transitions from the component this given input automata, and then I should have a disjunction here, right? Delta of Q0A. I can go to either directly. So suppose you have here Q11, Q21. Here you have Q12, Q22. Then essentially delta of Q0A should have Q11 and Q21. So I'm assuming this here they are in conjunction, or Q21 and right. So this is what we should do.
But that root node is Q01 and Q02, right? Not just Q0.
No, the root node of the input automata Q01 and Q02. But now I'm saying that when I'm constructing the automaton which will take care of the union, that will have a root node Q0, right? Q0, and I will have a transition from Q0, right, on this letter A, which will be given by this.
Okay.
Which will be given. So I look at the transitions from the initial state of the input automata, right? I look at them and I do their disjunction, right? So that's how I get the Boolean formula. Clear?
Okay.
So this is okay. I should say this is delta 1 of this or delta 2 of this here, right? Is it clear? So delta 1 of this or delta 2 of this. Okay. And for the other ones remain the same. Delta Q of A equal to delta I Q of A for Q belonging to Q1 union Q2. Clear? And I belonging to 1, 2. So all the other transitions, they remain as is. Okay, so only I need to add this special transition from the initial state. So this is for the union. And similarly for the intersection, everything is the same, but now I have the initial state, but instead of a disjunction, I add a conjunction. Okay? Is it okay? Okay, so this is this. So that is that, and then you can formally prove, of course, that the language accepted by this automaton is indeed the union of the languages of these two automaton, and similarly for the intersection, right? So